Thanks for asking the interesting question. I think if I just have to describe that paper, let's first try to understand what is machine learning in general. So in a machine learning setup, what you do usually is that you are given a bunch of data points or examples. And now what you do is you try to train a machine learning model on top of it. Initially, what you assume is that that data set is fixed, and that is what a lot of machine learning is all about. So you are given a data set, now you try to develop some algorithm on top of it that elicits the desired behavior. In our case, what we are doing is, instead of trying to do this machine learning in this way, what we are trying to tackle is the problem of internet scale data. In internet scale data, you have a lot of data points, and no person on this earth can actually go and look at those data points. So that means what we need is automated techniques that allow you to audit and understand these data sets in a better way. And the reason why you want to understand these data sets is actually very essential. For example, if you just look at examples like large language models, people have been using stuff like ChatGPT. And if you just try to understand what kind of biases, what kind of stereotypes, what kind of harmful content these models can produce, what you want to do is you want to be able to pinpoint these data points that the model was trained on and produce the desired or the harmful behavior that you want to remove. And if you just want to remove that behavior, maybe the best way is to actually be able to understand those data points that you train your model on and essentially remove those data points in a later iteration of your model. And what our work is mainly about is just trying to give you, using machine learning, trying to give you some tools that allow you to audit or understand larger scale data sets. Interesting question. I think it mainly started out of curiosity. What we were trying to understand is, given different sub-distributions or given different kind of data points, like typical examples, atypical examples, mislabeled examples, how does model training respond to these different kind of examples? So what we were trying to do is just monitor how the learning evolves over these specific kind of examples. And what we realized was that actually it's a lot more general than what we initially thought. Initially, it was just trying to understand what happens in the network. But then we realized that it's not just the points that we actually put into the model, but these traces in terms of loss trajectories or anything that you plot were actually very consistent across different examples in a particular category. And that's precisely what we leverage to develop our full methodology, where we have these different probe examples or probe categories. And now we try to surface similar examples. And the way we surface similar examples is just by matching the loss trajectory or loss traces across training time, and then try to surface similar examples. I think there were a lot of key decisions involved, like, for example, what kind of trajectories you use. Initially, we were trying to actually replicate one of the papers, and then we started with some GMM kind of approach, like a Gaussian mixture model, but then we realized that it was not the core of our approach, and we can get away with just discarding that approach and actually do something which is just full trajectory, rather than the last checkpoint that you have. And then once we generalized this framework, I think we got a lot of performance boosts out of it. So instead of focusing on that particular problem, we actually generalized it towards trying to solve a larger class of problems. And I think that, like, the main setbacks are like, in this case, we're just trying to generalize this. I think there were definitely setbacks at a few points, and I think those setbacks were not really due to anything else, but we just being stuck on a particular setup. Initially, we just started with very particular setup, and then we tried to focus on that particular setup. But then we realized that if we just try to generalize, or if we not try to focus on that particular problem that others are trying to solve, but instead take a more holistic view or try to focus on the larger problem, then we can do a lot better than we were what we were initially able to do. So that was the main thing that we were able to leverage over time. So though I won't count them as setbacks, but rather just blockers over time. So we just got blocked, or we just weren't able to see beyond that at that particular point. But the the moment we were able to see beyond that, we realized, okay, this is not the most important part. And then we had, like, I think the results part was, once we developed the full methodology, I think it was pretty straightforward to just get everything else to align up in terms of the results, because we already have done a lot of work before that on particular problems. So once we have the full general framework that actually worked, then it was easy to apply it to different problems. I think in research, you don't really know how the project will end up. Initially, you start with something which is an initial hypothesis, and over time you gather more information, and over time your hypothesis also evolves in terms of trying to understand the behavior that you're after. Initially, we started with something which was very, very interesting or out of curiosity, but it wasn't something of practical relevance. But over time, over several different iterations, we realized that we could transform it into something which is a lot more general and which allowed people to actually do large-scale data auditing. I think it can, right now, of course, as a researcher, you always believe that your work carries some significance. And I think this is not just me, this is every researcher who does anything. But I think right now my current belief is that it can have large implications for stuff like privacy. And this is something that we are trying to investigate. So how does it relate to privacy? How does it relate to stuff like, for example, deception? And a very preliminary way of understanding deception is data set poisoning. And then we can also try to understand how large language models evolve and try to audit actually large-scale data sets. And this is something that we are also trying to pursue in terms of trying to actually put that to use to understand internet-scale data, which is a language model that is trained on it, and then try to understand these different sub-distributions and potentially also improve downstream performance by focusing on the data points that you would like to potentially train on. I think there are a lot of exciting problems that I'm working on right now. A lot of them are actually very much related to what we did in the Metadata Archaeology paper. So, like, we are trying to work on an NLP extension of what we already did. Then we are also trying to think about different sub-problems that can actually be tackled with this framework, and then also trying to improve how we can potentially do this in a more efficient way. And then another line of research that I'm thinking about is just trying to understand generalization in a better way. So, for example, if you try to have different contrived setting of synthetic data sets, how does the model learn 3D generalization in those cases? So this is another stream of research. And finally, I think large language models in general, like, I'm really excited about what the capabilities of these models are, as everyone else is, and just trying to understand them in a better way. Their capabilities, their weaknesses, how they evolve to that point where you have such capabilities. Can you understand them in a better way? Can you actually improve these models?